Good afternoon. Today we're going to talk about acid-base chemistry titrations. I'm going to do this to help you with the alkalinity lab. There's 3 sections to this. Theory, where we talk about what the titration curve will look like. The lab, that defines what samples we'll be looking at during our titrations. And the analysis by MATLAB. The first video will focus predominantly on the theory, where we will cover potentiometric strong base and weak base titrations using hydrochloric acid as a strong acid titrant. We'll define a term called F. Then we'll move to the diprotic acid-base system, where we'll focus on the carbonate system and the concept of alkalinity and how it examines the titration of the carbonate system. And then finally, we'll look at some indicators. So we're going to start with a titration of a sample of sodium hydroxide with hydrochloric acid as the titrant. In the lab, we used a burette. We filled the burette with hydrochloric acid, and we took a volume of sample, 100 milliliters of sodium hydroxide, put it in a beaker, and we added the titrant, hydrochloric acid, dropwise. But in class I told you there was another way to look at this titration, which is to create a series of beakers to which we add 0.001 molar sodium hydroxide to each one and 100 milliliters of that solution. So all of the beakers start out the same. To the first, we don't add any of the acid. To the second, we add a small amount, or in this case 0.5 milliliters of hydrochloric acid. To the second beaker, or third beaker I should say in this case, we add 1 ml of the strong acid, and then we continually add larger amounts or larger doses of the hydrochloric acid to each successive beaker. We then solve the series of acid-base problems that we've created in each of these beakers to develop the titration curve. The species in our system are H2O, H+, and OH-, of course. We add hydrochloric acid to the system, but remember, hydrochloric acid is a strong acid, so there is no hydrochloric acid at equilibrium. Therefore, we only have chloride as the species coming from the hydrochloric acid. Similarly with the sodium hydroxide, we get Na+ and the OH- that we identified earlier. So those are the species in our system. We have 2 equilibrium reactions we could consider: the Kw, or hydrolysis of water, and the hydrochloric acid. But since we eliminated hydrochloric acid from the system, there is no reaction with it at equilibrium, so it gets deleted. We then have 2 mass balances, one on the acid that we added, which is hydrochloric acid, where we do the mass balance on the chloride, because that's the species coming from that. And remember, there's no hydrochloric acid, so the only species that contributes to that concentration in the system at equilibrium is chloride. And that concentration is variable depending on which of the beakers we're focusing on. So, for example, initially it would equal 0, and the next it's going to equal an increasing amount, so say 5 times 10 to the minus 4 molar. We could then add 1 at 10 to the minus 3 molar, and say 1.5 times 10 to the minus 3 molar, and so forth. We could add varying amounts. In contrast, the sodium hydroxide is constant in all of the beakers because we added the same amount to each one, and that concentration is 10 to the minus 3. And again, in this case, the sodium hydroxide is completely dissociated, so CTNA equals Na+, and that's equal to 10 to the minus 3 molar. Finally, the last equation is the charge balance, where you have the concentration of chloride plus the concentration of hydroxide equals the concentration of the proton plus the concentration of the sodium ion. Remember, the units of each term in the charge balance are moles of charge per liter. Moving along the titration curve, we're going to start at concentration of acid added being 0. Okay. We write our charge balance then, which won't have the chloride because there's no acid added. And we have H plus Na plus equals OH minus. We know the concentration of Na plus is equal to 10 to the minus 3. And we also know we're adding an acid, so our expectation is that the hydroxide concentration, we're adding a base, so the H plus concentration is small, and therefore we can write that Na plus is equal to OH minus and equal to 10 to the minus 3 molar. Okay, so we now know the Na plus concentration and the OH concentration. We can find the pH by first finding H plus from the Kw. So Kw is equal to hydroxide ion concentration times the proton concentration. Rearranging, we can write that H plus is equal to Kw, or 10 to the minus 14, divided by 10 to the minus 3 from the hydroxide concentration, and therefore hydroxide is equal to 10 to the minus 11. And the pH then will be 11. So we have our starting point for the titration. Moving on, we have 0.5 milliliters of 0.1 molar hydrochloric acid added to a 100 ml sample. The first thing we need to do is figure out what concentration of acid we added. So we use M1V1 equals M2V2. Rearranging to solve for M2, which is the concentration of acid we're adding, gives us the volume of 0.5 milliliters times the concentration of 0.1 molar divided by the 100 ml sample. We assume that the addition of the acid is negligible, so we just use the 100 milliliters, and we end up with a concentration of 5 times 10 to the minus 4 molar for M2, which is our concentration of acid. Okay, so moving on, we can now look at applying this to our charge balance, where we have H plus, OH minus, Na plus, and Cl minus. I move the OH minus to the left side of this equation, as you see, and I have H plus minus OH minus plus Na plus equal to the concentration of acid, which is equal to the chloride concentration, which is equal to 5 times 10 to the minus 4 molar. Okay. Again, I'm going to assume that the proton concentration is small, and so I have minus OH plus Na plus. Did I say OH minus? I meant to say the concentration of H plus is small because I haven't added that much acid. So I have the concentration of OH, the negative of that, plus Na plus is equal to the amount of acid that I've added, or Cl minus. Rearranging, since I know the sodium concentration, I can solve for OH. So I get OH minus is equal to the sodium concentration of 0.001 minus 0.0005, or my acid concentration, and that also equals 5 times 10 to the minus 4. So I now have the hydroxide ion concentration. So I can write again, Kw is equal to OH minus times H plus, solving for H plus, equal to 10 to the minus 14, divided by 5 times 10 to the minus 4, which is the hydroxide ion concentration, equals 2 times 10 to the minus 11, or 10 to the minus 10.7, and therefore my pH is equal to 10.7. So by adding 5 times 10 to the minus 4 molar of hydrochloric acid, my pH went from 11 to 10.7. Okay. Moving on, remembering still that the Na plus concentration is 10 to the minus 3 because it's the same in every beaker. I now add 1 ml of 0.1 molar HCl to this new beaker, and again 100 ml sample, and again I neglect the volume change. I use M1V1 equals M2V2, or 1 milliliter times the 0.1 molar divided by 100 milliliters to solve for M2, which is equal to 10 to the minus 3 molar. So again, I use my rearranged charge balance, H plus minus OH minus plus Na plus equal to the concentration of acid, which is equal to the chloride concentration, which is equal to 10 to the minus 3, as I've just calculated. I know the sodium concentration of 10 to the minus 3, so I rearrange and I get H plus minus OH minus is going to be equal to 0, since these two terms will cancel out. So in other words, H plus equals OH minus. Using Kw, I get that H plus is 10 to the minus 7, or in other words, my pH is equal to 7. Finally, now I'm going to add 1.5 milliliters of 0.1 molar HCl to our 100 ml sample. Again, neglect the volume, and again apply M1V1 equals M2V2. I get 1.5 milliliters times 0.1 molar divided by 100, where I've now added 1.5 times 10 to the minus 3 molar as my concentration of acid that I added. Applying that to my charge balance, my rearranged charge balance, I get H plus minus OH minus plus Na plus equals the concentration of acid, which is the same as the chloride concentration because hydrochloric acid completely dissociates, and that's equal to 0.0015 molar. Okay. Now I'm going to assume that OH is small because I was at pH 7 and I added more acid. So H plus Na plus equals 0.0015. Again, I know the sodium concentration is 10 to the minus 3, so I can rearrange this to get that H plus is equal to 5 times 10 to the minus 4 molar, or 10 to the minus 3.3. And now my pH is equal to 3.3. So what does this look like when I start plotting it all up? Well, I solved it for a whole bunch of different additions of hydrochloric acid, so I have a whole series of beakers here, where here's the milliliters I've added, and using M1V1 equals M2V2, this column is the moles of hydrochloric acid I have per liter, or in other words, that I've added. This is my chloride concentration in each case, or the amount of acid that I've added. So let's take a look. When we started, we said the initial pH was 11. We then started titrating. We looked at several samples, and one of this I want to point out, is when I added 1 milliliter, and when I added 1 milliliter, the moles per liter of hydrochloric acid I added was 0.01. That was the same concentration of sodium hydroxide that I added to the system. In other words, at this point, where I have this pH of 7 as my solution, and I added 0.001 moles, I reached an inflection point. This inflection point is, in fact, the equivalence point of my system, of my titration. And what it says is, this is where the amount of acid I added is equal to the amount of base I had initially. So, given that I know the milliliters of acid, I can apply M1V1 equals M2V2, as I did previously, to identify the concentration of NaOH that I had initially. That's how I do a titration. Again, if I employ the system using M1V1 equals M2V2, I know the milliliters of acid I added, and I know the molarity of the acid, I know the volume of the acid, and I know the volume of the sample. So substituting, this can be M1 is the M of the acid, V is the V of the acid, V2 is the volume of the sample, and what I'm solving for is M2 in this case, which is the concentration of base initially. So these are my knowns: molarity of the acid, volume of the acid, which is 1 milliliter at the equivalence point, which was 0.1 molar. The volume of the sample was 100 milliliters, and I can rearrange this to determine the concentration of base that I initially had in the system. That's how I use a titration. Okay, let's try the next one, which is the sample of sodium acetate, which is the weak base with the hydrochloric acid titrant. In this case, my species are H2O, H+, and OH-, as well as both the acid and the base for the weak acid-base system, HAC and AC-. Oops, no minus there. Get rid of that guy. And I also have Na+ from the sodium acetate and chloride from the HCl that I'll be adding. I have two reactions I have now that I have to keep both of, Kw and the HAC dissociating to AC- plus H+. So I have Kw and Ka. I have three mass balance equations, one on the acetate, HAC plus AC-. I'm going to add 10 to the minus 2 molar here to each of my beakers, okay? And I'm going to add a constant amount of that, and so both the Na concentration and the AC minus concentration will be identical. This is important because it will allow us to substitute in the charge balance, given that Na plus will have to equal the total of HAC plus AC minus. The amount of chloride I add, which is the concentration of hydrochloric acid, again is going to be variable and different for each of the beakers. So say 0, 5 times 10 to the minus 4 molar, 5 times 10, or 10 to the minus, or sorry, let's make that minus 3 molar, 10 to the minus 3 molar, and 1.5 times 10 to the minus 3 molar, or any other concentrations I wish to look at. All right, let's put some reasonable ones here. 10 to the minus 2, like that, 10 to the minus 2. Okay, now we're consistent with moving along the titration curve. So 0, 5 times 10 to the minus 3 molar, 10 to the minus 2 molar, and 1.5 times 10 to the minus 2 could be the representative concentrations that correspond to each of these beakers. Again, the charge balance is chloride plus acetate ion plus hydroxide equal to hydrogen ion concentration plus the sodium ion concentration. And again, the units of the charge balance are equivalents of charge per liter. Okay. So at the start of the titration, there's no Ca, which means there's no chloride, so my charge balance just has the hydrogen ion concentration, the sodium ion concentration, the hydroxide ion concentration, and the acetate ion concentration. Remember, CTNA is equal to Na plus, which is equal to 10 to the minus 2, and CTAC is equal to HAC plus AC minus, also equal to 10 to the minus 2. That means I can substitute HAC plus AC for Na plus in the charge balance, and I get H plus HAC plus AC minus equal to OH minus plus AC minus. Getting rid of the AC minuses because they cancel out, I get H plus HAC equals OH minus. Taking the logs of both sides, I can find the solution using my log CPH diagram, where HAC is represented by this curve here, and the OH is here, so I have H plus AC equal to OH minus, and there's my solution, which we've solved in class previously. So again, my left side dominated by HAC when I get to the solution point, and OH minus for the right-hand side. Okay. Now let's add 5 mils of 0.1 molar HCl to 100 mil sample. Applying M1V1 equals M2V2, we get that the concentration of acid added to the system, Ca, is now equal to 5 times 10 to the minus 3 molar. So rearranging the charge balance, H plus minus OH minus plus Na plus minus AC minus equal to the chloride concentration, which equals 5 times 10 to the minus 3. So looking at this equation, I know the concentration of Na plus, so I can rearrange this to say that OH minus plus H plus, OH minus H plus AC minus is equal to 0.01 molar, which is the Na concentration, minus 0.05 is equal to 5 times 10 to the minus 3. So that corresponds to the pKa. In other words, at this point, I have added half as much acid as base that I started with. The AC minus was initially 10 to the minus 2, and I end up having converted half of it, or I'm at the pKa. Okay? Moving on again, now I'm going to add 10 mils of 0.1 molar HCl to 100 milliliters, which will give me, using M1V1 equals M2V2, a concentration for the concentration for the acid of 10 to the minus 2. In other words, I'm adding the same amount of acid as base that I began with, so my charge balance can be written as H plus minus OH plus Na plus minus AC minus equal to chloride concentration, or equal to 0.01. So I have H plus minus OH minus plus Na plus minus AC equals 0.01. Knowing that the Na plus concentration is 0.01, I can write this as OH minus minus H plus plus AC minus equals 0. Or in other words, H plus equals AC minus plus OH minus. So I have H plus equal to AC minus plus OH minus. Okay. When I plot this charge balance, when I plot this left-hand side, log of H plus equal to the log of the right-hand side, my solution comes out right here. So this point corresponds to the equivalence point of the titration. And in this case, the equivalence point again is equal to the point where the amount of acid that I added is equal to the amount of base that I had initially. And what you can see using the log CPH diagram is that I converted a system that was representative of having added the base to the system to one that is now equivalent to having added the acid in the first place. If we look at this in terms of a titration, again, I've added a lot more points. The initial part of my titration, starting at that 8.36 that we saw on the, or 8.35 that we saw on the log CPH diagram. Then moving to our first inflection point that you can see right here. Notice that the first inflection point goes in the opposite direction of the one that we saw initially, and it corresponds to the pKa of the system. Oops, didn't mean to do that. And so if we look at that system, there is where we've added 5 mils. We've added 0.05 moles per liter of HCl, which is half the concentration of base that we initially added. We end up at the pKa. Okay? So you see the inflection point. And at this point, what this is showing you is that you can add a lot of acid without a lot of change in pH. This is a well-buffered system at the pKa. In contrast, when you go to the point where we've added the same amount of acid, 0.01 moles per liter, as base that we added initially, we see the other inflection point right here at about pH 3.36. And at that point, what you notice is that for just a little bit of addition of acid, we get a very steep or very big increase or change in the pH. So we get a very rapid change in the pH. So that's a monoprotic acid titration. Okay. The other thing that's kind of an interesting thing to do is to define what's called the equivalent fraction. So now I'm just taking the same data that we just saw, milliliters of acid added, moles per liter using M1V1 equals M2V2, pH that we determined based on solving the acid-base problem. And I'm going to define something called F. And this term F is the equivalent fraction. What it means is it's the concentration of strong acid that I titrated divided by the total concentration of base, the total concentration of base I had initially. So in our case, it's the concentration of hydrochloric acid I added divided by that concentration of the base, which was 0.01. Okay? And what's nice about the concept of F is that when you look at it, when you get to an F value of 1, you've added 0.01 moles per liter of acid, which is the same as the base concentration that you started with. Okay? When you look at the F value of 0.5, what you'll see is that you've now at the point where you've added half as much, 0.05 moles per liter of acid. So you've added half, and at that point you ended up at the pKa. So we define this term F. We can use the charge balance to determine the numerator, the hydrochloric acid added. So remember our charge balance was H plus minus OH plus Na plus minus NaC equal to the chloride concentration, which is the HCl added. We can also do our substitution for Na plus, knowing that the amount of Na plus that I initially added was equal to the total amount of acetate and HAC that I have. And so doing that substitution, what we find is that HAC plus H plus minus OH is equal to the chloride added to the system, or the HCl that I added. Okay? So F is essentially these terms, which go in the numerator, divided by the total concentration of base or acid that I had initially. These should be B's. Sorry about that. I can't change them. So this is the 0.01 sitting at the bottom, the CTB. And so I have HAC minus OH, or sorry, oof,